This is the 18th video in a series devoted to complex analysis, and we're going to go over a couple of things in this video. We'll go over what it means for a function to be analytic at infinity, as well as looking at the zeros of analytic functions. Okay, so for that first topic, we need a definition. So let's say a function f of z is analytic at infinity, so that's the phrase that we're defining, if f of 1 over z is analytic at 0. So that's good. We've put this new definition in terms of something that we totally understand already. But if f of 1 over z is analytic at z equals 0, that means it has a Taylor expansion about z equals 0. So that means we can write f of 1 over z as the sum as n goes from 0 to infinity of a sub n z to the n for some z modulus less than r, where that's our radius of convergence. But then composing back in the 1 over z function to expand this about infinity, if you will, we get that f of z is equal to the sum as n goes from 0 to infinity of a n over z to the n, or maybe a sub n times z to the minus n. But then, since we replaced z with 1 over z from here to here, that means that now our radius of convergence is a bit different. We have the modulus of z is strictly bigger than r. And so that means it converges on a region outside of a disk instead of inside of a disk. But still, we don't know exactly what's going on with the boundary. That has to be tested on a case-by-case basis. Then we can calculate the coefficients as follows in terms of the original function. And so this is just adapted from what would be going on up here. So we have the nth coefficient is 1 over 2 pi I times the integral around a circle with radius r centered at the origin of z to the n minus 1 times f of z dz, where this little r is bigger than this r, so that we're in an analytic region. Okay, so let's go through a couple of examples of this before we look at zeros of analytic functions. So we'll start with the function f of z, which is 1 over 1 minus z. So we know that this can be expanded via a geometric series as the sum as n goes from 0 to infinity of z to the n, where the modulus of z is less than 1. So that would be at a series expansion about z equals 0. But this thing is also analytic at infinity, which we can check using our definition over here. So let's look at f of 1 over z. Notice that that is 1 over 1 minus 1 over z. But then we can simplify this a little bit by multiplying by z over z, and that's going to give us z over, let's see, z minus 1, which is most definitely analytic at z equals 0. So f of 1 over z is analytic at z equals 0. That tells us that our original function f of z is analytic at z equals infinity. And so now let's see if we can expand it about z equals infinity and see what we get. So we can write f of z, which is 1 over 1 minus z, maybe like this. So we have 1 over 1 minus z. Let's instead write this as 1 over z over 1 over z minus 1. So what did we really do here? We multiplied the numerator and the denominator by 1 over z. So now it looks like this guy right here, where we've just replaced z with 1 over z, and we can take an expansion of this where we're viewing the 1 over z as like a variable in its own. So maybe we'll factor out a minus 1 over z, and that leaves us with 1 over 1 minus 1 over z. Like I said, we're going to think about that 1 over z as a variable of its own, and we can expand that as a geometric series. So that gives us minus 1 over z, and then we have the sum as n goes from 0 to infinity of 1 over z to the n. So in the end, we can just leave the minus sign out front, and we have the sum as n goes from 0 to infinity of 1 over z to the n plus 1. And this is valid in the region where z is bigger than 1, so outside of that unit disk. Okay, so I think this is a pretty interesting relationship here between these two functions. So here we have this thing expanded as a geometric series in powers of z, and the convergence is inside the unit disk. Here we have this thing expanded as powers of 1 over z, and that's convergent outside of the unit disk. Again, we don't have anything which is true on the unit disk, however. Okay, so now that we've got this example, let's move on to the second topic of this video, which, like I said, is zeros of analytic functions. So we've got two definitions related to zeros of analytic functions to start with. So let's suppose that z is analytic at z naught. Then we say that f has a zero of order n at z naught if f evaluated at z naught is 0, f prime evaluated at z naught is 0, all the way up to the n minus first derivative of f evaluated at z naught is 0. So we've got n total objects related to f evaluated at z naught is equal to 0. But that's equivalent to the Taylor expansion of f about z naught starting with the nth term. So it starts with an z minus z naught to the n, then we have an plus 1 z minus z naught to the n plus 1, and so on and so forth. So we've got an infinite tail in that direction. And I didn't write this, but sort of the undercurrent here is that a sub n is not equal to 0, because then we would have a 0 with greater order than n. Okay. But notice that that is equivalent to f of z being able to be written as z minus z naught to the n times g of z, where g does not have a 0 at z naught, and it's analytic at z naught. So we'll use each of these kind of as needed. Then next, we say that f of z has a 0 of order n at infinity if f of 1 over z has a 0 of order n at 0. So just kind of in line with how we defined a function to be analytic at infinity. Furthermore, that means its power series expansion at infinity looks like this. So it starts with the nth term. We've got an over z to the n plus 1 over z to the n plus 1, and so on and so forth, that infinite tail. Okay, so let's look at an example. And so we're going to look at the function f of z, which is equal to 1 over z squared plus 1. And let's notice that this has a 0 at infinity. We can maybe see that it has a 0 at infinity intuitively by noticing that f of infinity. So I'll put this in quotes because this is kind of sketchy. That's the limit as z goes to infinity of f of z is equal to 0, just based off of the definition of f of z here. But let's look at it via the careful definition. We'll calculate f of 1 over z, and we'll see that that is equal to 1 over 1 minus z, or 1 over z squared plus 1, which we can maybe multiply the numerator and the denominator by z squared, and we'll see that this is equal to z squared over z squared plus 1, which is finally equal to z squared times 1 over z squared plus 1. And this guy right here is playing the role of g of z in our definition over here. So if we evaluate g at 0, we do not get 0. And so since we factored out this z squared, we know that we've got a second order 0 at z equals infinity. Okay, so furthermore, we can expand this at infinity using like a standard rules for expanding geometric series. So let's take the original f of z and let's rewrite it like it looks like a function of 1 over z. So we can do that by rewriting it as 1 over z squared times 1 plus 1 over z squared. Then we've got, this is like a geometric series where the starting term is 1 over z squared and the common ratio is negative 1 over z squared. So this expands as 1 over z squared times the sum, as in goes from 0 to infinity of minus 1 to the n over z to the 2n. So we're left with something like that. So that would be the expansion of this thing about infinity. So let's notice that this expands out as 1 over z squared minus 1 over z to the 4th plus 1 over z to the 6th minus 1 over z to the 8th plus dot, dot, dot. So the expansion starts at the 1 over z squared term, sort of reinforcing this result that we have up here, that this has a second order 0 at z equals infinity. Okay, so now that we've looked at this example, I'm going to replace this definition with something else, and then we'll start proving general results. So next we're going to give a little bit of a topological definition inside of the complex plane, and that is the notion of an isolated point. So given a set of complex numbers, which we'll call A, we say that a point z0 in A is an isolated point if there exists a delta bigger than 0 such that the ball around z0 of radius delta intersected with A, so we can put that here as just taking z from A, only contains z0. So that means that we have got some sort of picture like this. So let's say A is given by this single point here and then the rest of these points over here. But notice that we can find some sort of disk to put around this point z0 where it doesn't touch the rest of the set A. So the only members from A that are inside of this disk right here is the point z0 itself. So eventually what we'll prove is that all of the zeros of an analytic function are isolated points. So there's no non-isolated set of zeros of analytic functions. But before we do that, we need kind of a starter result, which says that if we've got f from a domain D to the complex numbers, which is analytic and not identically 0, then its zeros are of finite order. So notice over here, we did not presuppose that the order n here had to be finite, although that's kind of written in the margin, if you will, but now we're going to prove it carefully. Okay, so we're going to do this by way of contradiction. So let's suppose that z0 is an element of our domain where it is a 0 of infinite order. So I'll just write it like that, a 0 of infinite order. So what does it mean to be a 0 of infinite order? Well, that means that f evaluated at z0 is the same thing as f prime evaluated at z0, which is the same thing as f double prime evaluated at z0, which is the same thing as the nth derivative evaluated at z0. In fact, all of the derivatives evaluated at z0 are equal to 0. So that's just based off of this definition over here. So now let's do the following. So if we have a single 0 of infinite order, then we've got at least a non-empty set of zeros of infinite order. It's at least that singleton. So let's collect them together into a set called U. So let's set U equal to all z in D such that z is a 0 of f of infinite order. So we can rewrite that as the nth derivative of f evaluated at z equals 0 for all n bigger than or equal to 0. So that's just kind of putting those words into a symbol. And again, like I said before, U is non-empty, and that's because this Z0 is an element from U based off of our assumption. Okay, so next up, since Z0 is in D and F is analytic on D, we can expand F as a power series based at Z0. So let's do that. So we can say F of Z equals the sum as n goes from 0 up to infinity of a sub n times z minus z0 to the n. But if you recall, we know a formula for a sub n, so let's rewrite that as the nth derivative evaluated at z0 over n factorial. So that means this equals 0 whenever we're within the radius of convergence. And so that's going to be for all z in D such that the modulus of z minus z0 is less than r, where that's our radius of convergence. Well, you might say, well, what's that R? And in order to get a feel for what that R is, let's make a picture. So let's say this is our domain D, and then down here is our point Z naught. And from something we did in a previous video, we know that that radius of convergence extends from the point Z naught as far as we can go before we hit a point where this function is not analytic. So here that would be like the boundary of D. So in this case, it looks like the closest boundary point is about right there. So our R would be the radius of this circle. But notice that this R is definitely bigger than 0 because D is an open set. So I'll just say that. We know that R is bigger than 0. But what does that mean? That means that f of z is identically the 0 function for all z on this open disk. But we fit an open disk inside of U. So we know that U contains at least this open disk. So we'll say U is this. But what did we do? We found an open neighborhood around an arbitrary point inside of U. That means that U is an open set. So here, we'll collect that information right here. U is an open set. Okay, but what have we not used yet? We haven't used the fact that f is not identically equal to 0. So let's use that now. So we'll take a z1 in D such that f evaluated at z1 is not equal to 0. Again, we can do that because we know that f is not identically 0. And so that's going to be definitely outside of this U. So we could maybe put it right here. So z1. And notice that f can have zeros outside of this U. It can just have not zeros of infinite order. But this isn't even a 0 because f evaluated at z1 is not a 0. Okay, good. But now we know that f is continuous because it's analytic. So let's find some delta bigger than 0 such that if the modulus of z minus z1 is less than delta, we have the modulus of f of z minus f of z1 is less than the modulus of f of z1 over 2. Well, why did I choose that? Well, I chose that because that bounds f of z away from 0. So that tells us that the modulus of f of z is strictly bigger than 0 for everything within that disk of radius delta. So maybe we can make that picture like this. We've put this disk of radius delta around z1, and the function is never equal to 0 inside of that disk. But what does that mean? That means that for any point outside of U, in other words, in D minus U, we can find an open neighborhood that's totally contained in D minus U. But what does that mean? That means that D minus U is also open. But that means we've got a disconnection of D by U and D minus U. So we have D is the union of U and the set difference of D minus U, both of which we have shown to be open sets. But given that D is a domain, we know it's connected, so that indeed brings us to a contradiction. Now, thinking about what our contradiction is, well, let's go back up to the point where we made an assumption, and that would be right here where we assumed that we have a 0 of infinite order, so that must not be true, and thus we only have zeros of finite order. Okay, so now let's move on to our next result. Now we'll build off that previous result by proving that with the same setup, all of the zeros of f are isolated. So we can read this very quickly as any non-zero function, so non-identically 0 function, which is analytic, has isolated zeros. Okay, so that's good. Let's maybe get to the proof here. So let's suppose that we have z0 in D, which is a 0 of f of order n. So it's a 0 of order n. But then by this third way of thinking about the zero of order n, we can write f of z as z minus z naught to the n times g of z, where g of z naught is not equal to 0, and further, g is analytic. But since g is analytic, it's continuous. But since g is continuous, we can play a pretty similar game to what we did before. So let's do that. So let's find some delta bigger than 0 such that if the modulus of z minus z naught is less than delta, we have the modulus of g of z minus g of z naught is less than the modulus of g of z naught over 2. So what does that tell us? That tells us that g of z is not equal to 0 for all z that are within delta of z naught. But now, since z minus z naught is only 0 at z naught, that tells us that f of z is not equal to 0 for all z minus z naught less than delta, as long as we are strictly bigger than 0. But that's exactly what we need for this z naught to be isolated. So z naught is isolated, right? We bound it away from any other zeros of f. So I'd like to point out that this is a pretty strong result that does not hold for real valued functions. It's a little bit tricky to write down the formula for this type of real valued function, but you can construct a smooth function that's an infinitely differentiable function that has the following behavior. So it maybe kind of does whatever, but then it smoothly eventually becomes a constant of 0. So this would be some sort of non-isolated set of zeros over here, which is not possible in the complex plane. So let's look at a nice corollary of this, and then I'll leave you with some warm-up exercises. So now a quick corollary and application of the previous theorem. So if f and g are analytic on a domain D, and the set of all points where f of z equals g of z contains non-isolated points, then f and g are the same function. In other words, they are equal for all z in D. Okay, so how would we see this? That's just the previous result applied to the function f minus g. So that's really all that needs to be said here. So here's a nice application. So let's say we assume from learning this in trigonometry or in calculus class that the cosine of alpha plus beta is the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta for all alpha beta between 0 and 2 pi. Notice that's a non-isolated set. It's because we've got a unit interval living in the real line, which is living in the complex plane. That means that we have cosine of z plus w is cosine of z, cosine of w minus sine of z, sine of w for all zw in the complex plane. That's because cosine and sine are analytic on the whole complex plane. Okay, so let's maybe finish off with some warm-up problems. So here's some nice warm-up exercises built off of what we did today. So the first is to expand the following 3 functions as a power series about z equals infinity. So we've got z over z plus 1, z squared over 1 minus z cubed, and then z times the sine of 1 over z. Next is to find the zeros and the order of these zeros, not forgetting about zeros at infinity, of the function 1 over z squared plus 1 over z to the 4th, 1 minus cosine z over z, and finally z squared times e to the minus z. And that's a good place to stop.